Dear students, after studying this module, you will be able to know the difference between a parameter and a statistic or estimator, and the need to obtain an estimate of an unknown parameter value. We would also be able to learn about the problems in identifying an estimator of a population parameter. You would also learn about the desirable properties of a good estimator and how to use these properties to identify the best estimator and obtain the required estimates. In the end, we would try to evaluate how precise is the estimate likely to be, because these are some of the questions we would be interested in from a sample statistics. So to begin with, any population is characterized by its parameters. If the form of the distribution is known, then the type of parameter is also known. A population distribution may be uniform or binomial or Poisson or exponential or normal or any other form. Now, different populations of the same type will differ in the value of the parameter. The parameters of the population can then be used to obtain the various characteristics of the population that are of interest in economic and business decision making, such as the mean and variance of the distribution. Now, whatever may be the form of the population, as long as the items belonging to the population differ in the value of the variable of interest, for example, daily sales of a firm, etc., the summary measures like mean and variance of the population values are valuable inputs in the decision-making process. First of all, we will therefore distinguish between a sample and the census, or the census and sample. Whereas population values required for calculation of the values of the desired characteristics can be obtained by taking a census of all population units. However, it is often the case that due to time and cost constraints, a census is not always feasible. In some cases, the population units being examined are destroyed in the process, as in the study of lifetime of, say, filament bulbs. So you want to find out the life of a bulb, you cannot destroy each and every bulb to find out its filament life. Therefore, an alternative to a full census study is a sample survey. If sufficient care is taken in the selection of the sample, then it will be quite representative of the population. In that case, the characteristics of the sample will then be representative of the population characteristics. A commonly used technique of sampling is the simple random sampling method. In the simple random sampling or SRS method, all sample units are said to be identically and independently distributed. We, in abbreviated form, denote them as IID. So what is IID? IID is identically and independently distributed units. Now, each unit of the population has an equal chance of being selected in the sample. Since any sample unit can be any one of the population units, each sample unit has the same probability distribution as that of the population. It is basically a matter of chance which particular population units get selected in the sample, as each unit has equal chance of selection. Therefore, the probability of selection of any sample unit is independent of which population units have already been selected for the sample. Also, all possible samples from the population are equally likely. If sampling is with replacement, then the conditions of a simple random sample are exactly satisfied. With replacement basically means that if I have drawn one item from the population, then I replace this item back with the population before I take another item from the same population. On the contrary, if the sampling is without replacement from a finite population, but sample size is small relative to population size, let's say not exceeding 5% of the population, then the conditions of IID are approximately satisfied. Next, we will discuss estimator and problems of estimation. A sample statistic or estimator is a function of sample observations, and the value of the sample statistic is called an estimate. An estimator gives us a formula to combine the sample values to obtain an estimate. An estimate is a particular value. The unknown population parameters can be estimated using the appropriate sample statistics or estimators. The problem in estimation, I am sure you would realize, are twofold. The first problem is that there may be more than one possible estimator for the same parameter. For example, sample mean, sample median, sample trimmed mean, or some weighted average of sample observations can all be used to estimate the population mean if the population distribution is continuous and symmetric. In such situations, a choice has to be made among the available estimators. The second problem is that different samples from the same population are unlikely to have identical sample units. Therefore, the chosen estimator will yield different estimates for different samples because of sampling fluctuations. So, different estimates for the same parameter will result from different samples of the same size from the same population. So, what we are saying is, if you take a sample of size 10 from a population of 100, you can have different samples of the same size 10, and each sample will give you a different sample statistic. Therefore, the question is, what are the answers to these problems, the first and the second? Let's understand the answer to these questions or the problems. The answer to the first problem is to first decide the desirable properties of a good estimator. We should know what are the properties we are looking for, and then select the estimator that satisfies the desirable properties and select the best among the alternatives which are available to us. Once such an estimator is selected, it can be used to obtain an estimate of the population parameter. Since a single value of the estimate is obtained from a single sample, this estimate of the parameter value is also known as the point estimate, because we have one value, so one point, and we call it as point estimate. And the statistics itself is called a point estimator. The answer to the second problem is not cite a single value as an estimate. Instead, a range of values centered at the point estimate can be used. Knowledge of the sampling distribution of the estimator enables us to set up an interval of values within which the parameter value is likely to fall. Thus, the point estimator, in combination with the characteristics of its sampling distribution, gives us the confidence interval estimator. So, we have the point estimator and we have the confidence interval estimator as the answers to both the problems, first and the second problem. In the selection of a point estimator, first we will discuss mean square error. The mean square error, or MSE, is defined as expected value of theta hat minus theta whole square, which is equal to sigma theta hat minus theta square into P theta I hat, where theta hat is the sample estimate of the population parameter theta and MSC is a measure of total variability of the estimated values about the true value of the parameter. Now consider two competing estimators, TO1 and TO2. It would seem that the estimator with the minimum value of MSC should be the preferred estimator, as that would provide a closer approximation to the true parameter value since it has lower total variability. The principle of minimum mean square error cannot be applied, however, for selecting the appropriate point estimator. The reason being that the MSE is itself generally dependent on the value of the parameter. We may find that for some values of theta, MSC tau 1 is less than MSC tau 2, whereas for other values of theta, the result is that MSC tau 1 is greater than MSC tau 2. So finding an estimator with the smallest MSC for all values of theta is not possible. We cannot therefore use the principle of minimum mean square error in the selection of the best estimator from among the several possible estimators. Hence, we need some other method for selecting the best possible estimator that is independent of the parameter value, when there is more than one possible estimator of the given parameter. We will now specify and explain the desirable properties of a good estimator and see how these can be used to select the best among the available point estimators of a population parameter. Whatever may be the population being studied, the estimator may be used to obtain an estimate of the unknown parameter value. The properties are unbiasedness, efficiency, consistency. First, we will discuss unbiasedness. The estimator theta hat is said to be an unbiased estimator of the population parameter theta if, for any sample size, expected value of theta hat is equal to theta for all theta. This means that if random samples of the sample size were repeatedly drawn from the population and the estimate theta hat was calculated, then on the average, the estimated value will exactly equal the true parameter value theta. This property does not imply that each and every sample will yield an estimate equal to theta. But on the average, with repeated sampling, we can expect the estimator to yield an estimate that matches the parameter value. Some estimates will be too large and others will be too small, but in the long run, there will be no systematic tendency to overestimate or underestimate theta. The above figure illustrates the symmetric distributions of unbiased and biased estimators theta 1 hat and theta 2 hat. The figure shows the difference between the sampling distributions of an unbiased estimator theta 1 hat and that of a biased estimator theta 2 hat. Bias of an estimator theta hat is measured by expected value of theta hat minus theta. Bias of an unbiased estimator is thus 0. Next, we will discuss skewed distributions of unbiased and biased estimators theta 1 hat and theta 2 hat. When expected value of theta hat minus theta is less than 0, there is a tendency to underestimate the parameter value. This does not mean that each and every sample will result in an underestimate. On the average, we can expect an underestimate. Similarly, if expected value of theta hat minus theta is greater than 0, there is a tendency to overestimate. Under unbiasedness property, first we will discuss unbiased estimator of population mean. An example of an unbiased estimator is the sample mean, which can be used to estimate the population mean. For a random sample of size n, the sample mean is denoted by x bar and the population mean by mu. In a random sample, each sample unit is independently and identically distributed. So each sample unit will have a probability distribution same as that of the population with mean mu. Now sample mean x bar is equal to sigma xi, I ranging from 1 to n, divided by n. And expected value of x bar is equal to 1 by n into expected value of sigma xi, where I ranges from 1 to n. This is equal to 1 by n into sigma of expected value of xi. This comes out to be equal to 1 by n into n mu, because expected value of each xi is equal to mu and therefore is simplified as equal to mu. So all this is on the basis of simplification and assumption that expected value of xi or expected value of sigma xi is same as sigma of expected value of xi. The sample mean is therefore an unbiased estimator of population mean. The sampling distribution of the estimator x bar is centered at mu, although each and every sample may not yield a mean value of mu. In the long run, however, the expected value of x bar is mu. Let us explain with the help of an example. Suppose a random sample of two observations, x1 and x2, are taken from a population with mean mu and variance sigma square. Show that the following 3-point estimators of mu are unbiased. First, x equal to half x1 plus half x2. Second, y equal to 1 by 4 x1 plus 3 by 4 x2. And third, z is equal to 1 by 3 x1 plus 2 by 3 x2. This can be solved as expected value of x is equal to expected value of half x1 plus half x2. This is equal to half into expected value of x1 plus half ex2 and is equal to half mu plus half mu equal to mu. Similarly, expected value of y is equal to expected value of 1 by 4 into x1 plus 3 by 4 into x2 is equal to 1 by 4 into expected value of x1 plus 3 by 4 into expected value of x2, and this comes out to be equal to 1 by 4 mu plus 3 by 4 mu, and hence is again equal to mu.
Similarly, you can see that expected value of z is equal to expected value of 1 by 3 x1 plus 2 by 3 x2 and is equal to 1 by 3 into expected value of x1 plus 2 by 3 into expected value of 2 and is equal to 1 by 3 mu plus 2 by 3 mu and hence is equal to mu. So since expected value of x is equal to expected value of y is equal to expected value of z and are equal to mu, all three are unbiased point estimators of mu. Let us now consider the estimator for population variance sigma square. Since sigma square is defined as sigma xi minus mu square, where I ranges from 1 to n is capital N divided by capital N for population size n. It may seem natural that the appropriate estimator would be sigma hat square equal to sigma xi minus x bar square divided by n. N is small n, which is less than the capital N, where x bar is an unbiased estimator of mu. Let us see if this is an unbiased estimator for sigma square. Expected value of sigma hat square is equal to expected value of sigma xi minus x bar square, where I ranges from 1 to small n divided by n, is equal to 1 by n into expected value of sigma xi minus mu minus x bar minus mu whole square. Now this on simplification comes out to be equal to 1 by n into expected value of sigma xi minus mu square plus sigma x bar minus mu square minus twice sigma xi minus mu into x bar minus mu. This is equal to 1 by n into sigma expected value of xi minus mu square plus sigma expected value of x bar minus mu square minus twice expected value of sigma xi into x bar minus n mu into x bar minus sigma mu xi plus n mu square is equal to 1 by n into n sigma square plus n into sigma square by n minus 2 expected value of nx bar square minus n mu x bar minus n mu x bar plus n mu square. This is equal to 1 by n into n sigma square plus sigma square minus 2n expected value of x bar minus mu square is equal to 1 by n whole bracket n sigma square plus sigma square minus 2n into sigma square by n bracket close. Now this on simplification is equal to n minus 1 upon n into sigma square. Now n minus 1 upon n is less than 1. This implies that expected value of sigma hat square is less than expected value of, repeat, n minus 1 upon n is less than 1. This implies expected value of sigma hat square is less than sigma square. Therefore, sigma hat square is not an unbiased estimator of sigma square. The measure of bias is expected value of sigma hat square minus sigma square and is equal to n minus 1 upon n sigma square minus sigma square. This is equal to sigma square into n minus 1 upon n minus 1. This is equal to minus sigma square upon n, which is less than 0 because it is negative. Thus, the estimator sigma hat square has the tendency to underestimate the population variance. However, as n tends to be infinity, minus sigma square by n tends to be equal to 0, and sigma hat square is asymptotically unbiased estimator of sigma square. So we can say the unbiased estimator of sigma square is S square, which is defined to be equal to sigma xi minus x bar square upon n minus 1. Since S square is equal to n upon n minus 1 into sigma hat square, and therefore expected value of S square is equal to n upon n minus 1 into expected value of sigma hat square, which can be rewritten as equal to n upon n minus 1 into n minus 1 upon n into sigma square, and therefore it comes out to be sigma square. So when sample size n is large, the bias of sigma hat square is small, and there is little difference between the two estimators sigma hat square and S square. Although S square is an unbiased estimator of sigma square, this does not mean that S is an unbiased estimator of population standard deviation sigma. This is because expected value of theta hat is equal to theta does not imply that expected value of any function of theta hat is equal to f theta, which is a function of theta. However, the bias of S is small unless n is quite small. This can be explained with the help of an example, as the following sample was taken from a population with mean mu and variance sigma square. The sample consists of the values 6, 8, 7, 10, 3, 5, 9, 8. The question is, find the point estimates of the population mean and variance. Solution. The point estimate of mean is mu hat is equal to x bar is equal to sigma xi upon n, where sigma xi is some of the deviations from arithmetic mean. And this comes out to be equal to 56 by 8 and is equal to 7. The estimated population variance is sigma hat square is equal to S square is equal to sigma xi minus x bar square upon n minus 1. On substituting the values from the sample, we find this is equal to 36 divided by 7 and comes out to be equal to 5.143. Next, we will discuss unbiased estimator of population proportion. The main consideration is the population proportion of successes. Let us denote population proportion by P and sample proportion by P hat and is equal to x by small n, where x is the number of successes in a sample of size n. If any outcome in the sample that cannot be classified as a success is considered to be a failure, all the outcomes are independent. The probability of success or failure is known and remain unchanged for all successes. Then, given n, the random variable x has a binomial distribution. Thus, expected value of x is equal to np. Therefore, expected value of p hat is equal to expected value of x by n is equal to 1 by n into expected value of x and is equal to 1 by n into np, which comes out to be equal to p, so that sample proportion is an unbiased estimator of population proportion. This can be better explained with the help of an example as a sample poll of 600 randomly chosen voters from all registered voters in a city indicated that 222 voters preferred a particular candidate for the post of mayor. What is the estimate of the percentage of the population in favor of this candidate? Solution: n is equal to 600, x is equal to 222. Therefore, p hat is equal to x by n is equal to 222 by 600 and is equal to 0.37. Therefore, it is estimated that 37% of all voters prefer this candidate for the post of mayor. Thus, the principle of unbiased estimation is, when choosing among several different estimators of theta, select one that is unbiased. Now we will discuss another desirable property, that is efficiency, or we can also discuss minimum variance unbiased estimation, denoted as MVUE. In the event that there exists only one unbiased estimator for a given parameter, the search for a good estimator ends there. However, if there are more than one unbiased estimators, then the best among these has to be selected. An example of multiple unbiased estimators exists for the population mean. If the population is symmetric and continuous, then the following are all unbiased estimators of the population mean. For example, sample mean x bar, sample median x eta, sample trimmed mean x tr bar, semi-interquartile range, etc. Choice of the best among unbiased estimators is based on the principle of minimum variance. The principle of minimum variance unbiased estimation is, among all the estimators of theta that are unbiased, choose the one that has minimum variance. The resulting estimator theta hat is called the minimum variance unbiased estimator, or MVUE, of theta. Suppose theta 1 and theta 2 are both unbiased estimators of the parameter theta. The sampling distributions of the two estimators will both be centered at the true value of theta, since expected value of theta 1 hat is equal to theta and expected value of theta 2 hat is also expected to be theta. However, the spread of two sampling distributions are not the same as shown in the given figure. Let variance of theta 1 hat is less than variance of theta 2 hat. As the distribution of theta 1 hat is clustered closer to theta than the distribution of theta 2 hat, therefore theta 1 hat is more likely than theta 2 hat to produce an estimate close to the true value of theta. In the choice between the two estimators, theta 1 hat is the preferred estimator, as it is the minimum variance unbiased estimator of theta. The minimum variance unbiased estimator is the most likely among all unbiased estimators to produce an estimate close to the true value of the parameter. The minimum variance unbiased estimator, or MVUE, is also called an efficient estimator. Efficiency is linked to economic cost of a sample. The most efficient estimator requires the smallest sample size for the same level of precision as any of the other estimators. Closer the estimate is to the true parameter value, greater is the precision of the estimate. This can be illustrated by comparing the sample mean and sample median, which are both unbiased estimators of the mean of a symmetric population. Variance of x bar is equal to sigma square by n, and variance of x zeta is equal to pi by 2 into sigma square by n, where sigma square is population variance and n is sample size. Comparing the variances of the two estimators, we obtain the efficiency ratio. The one with the smaller variance, that is efficiency ratio greater than 1, is said to be the efficient estimator. The relative efficiency or efficiency ratio of x bar with respect to x zeta is the ratio variance of x zeta upon variance of x bar. Thus, the relative efficiency of x bar to x zeta is equal to variance of x zeta upon variance of x bar is equal to pi sigma square by 2n upon sigma square by n, and is equal to 1.5714. Since the sampling distribution of the median is more spread out than that of the sample mean for the same sample size n, to reduce the dispersion in distribution of the median so that of the mean, the sample size has to be increased substantially by a factor of 1.57 or by 57%. Increase in sample size increases the cost of the study accordingly. The minimum variance unbiased estimator is therefore the most efficient unbiased estimator. Note that in some situations, theoretically, an estimator with a small bias may be preferred to the best unbiased estimator. As illustrated in the figure, we consider an unbiased and efficient estimator theta 1 hat and a biased estimator theta 2 hat. But variance of theta 1 hat is greater than variance of theta 2 hat. Bias of theta 2 hat is equal to expected value of theta 2 hat minus theta 2. The distribution of the biased estimator is clustered close to the true parameter value and has a higher probability of giving an estimate very close to the true value. However, it is more difficult task to search for unbiased estimators. The minimum variance unbiased estimators are often easier to obtain and are normally used. Now explaining it better with an example, as of the three estimators of mu in example 1, which one is the best estimator? Solution: x is equal to half x1 plus half x2, y is equal to 1 by 4 x1 plus 3 by 4 x2, z is equal to 1 by 3 x1 plus 2 by 3 x2 are the three unbiased estimators of population mean. We compare their variances to select the best estimator, that is the minimum variance unbiased estimator or the efficient estimator. Now variance of x is equal to 1 by 4 variance of x1 plus 1 by 4 variance of x2. This is equal to 1 by 4 sigma square plus 1 by 4 sigma square is equal to half sigma square or is equal to 0.5 sigma square. Similarly, variance of y is equal to 1 by 16 variance of x1 plus 9 by 16 variance of x2 is equal to 1 by 16 sigma square plus 9 by 16 sigma square, and this is equal to 10 by 16 sigma square and is equal to 0.625 sigma square. Similarly, we can find out variance of z and is equal to 1 by n variance of x1 plus 4 by 9 variance of x2. Now this is equal to 1 by n sigma square plus 4 by 9 sigma square and is hence equal to 5 by 9 sigma square, which is equal to 0.555 sigma square. On comparing the three, we find that since variance of x is less than variance of z is less than variance of y, x is the best estimator. It is the most efficient of the three estimators. Notice that estimator x is the mean of the sample. Therefore, it is the minimum variance unbiased estimator of population mean. The last desirable property is consistency. In the absence of unbiased estimators, we can opt for a consistent estimator. A consistent estimator may not be unbiased when sample size is small, but as sample size increases, it tends to become unbiased. We are saying an estimator is said to be consistent if for any epsilon greater than 0, probability of modulus theta hat minus theta is greater than or equal to epsilon, which tends to be equal to 0 as n tends to be infinity. Consistency is therefore a large sample property. As sample size increases, the difference between the expected value of the estimator and the true value of the parameter decreases. An example of a consistent estimator is sigma hat square equal to sigma xi minus x bar square, where I ranges from 1 to small n, divided by n. As sample size increases, bias, which is expected value of sigma hat square minus sigma square and is equal to minus sigma square upon n, approaches 0. A consistent estimator is asymptotically unbiased. If there is more than one consistent estimator, then the one with minimum variance should be chosen. Next, we will discuss the precision of an estimate. Given sample data, the unknown parameter value can be estimated using the selected estimator. Besides reporting the point estimate, it may be desirable to indicate how precise the estimate is. In other words, how close to or far away from the true parameter value is the estimate likely to be. The usual measure of precision of the estimate is the standard deviation of the sampling distribution of the estimator, also called the standard error of the estimator. The standard error of the estimator theta hat is defined as sigma theta hat and is equal to under root of variance of theta hat. Smaller the standard error, narrower is the spread of the distribution, and more likely is the estimate to be close to the true value of the parameter. Larger the standard error, greater is the spread of the sampling distribution, and correspondingly, the likelihood of a precise estimate also decreases. Thus, the standard error tells us roughly within what distance of theta hat we can expect the value of theta to lie. If sigma theta hat involves unknown parameter values that can be estimated, we can substitute these estimated values to obtain the estimated standard error in such cases. The estimated standard error can then be denoted as sigma hat of theta hat or S of theta hat. Take for example the sampling distribution of X bar, the minimum variance unbiased estimator of population mean mu. Now sigma X bar is equal to sigma upon root n, where sigma is the population standard deviation. Since mu is unknown, sigma would most likely be unknown. Then we need to substitute the sample estimate of sigma in the formula for sigma X bar, and we get the estimated standard error S X bar and is equal to S upon root n. Similarly, the standard error of the distribution of sample proportions is sigma p hat and is equal to under root of pq by n. With unknown parameters p and q equal to 1 minus p. As these are unknown, we can substitute p hat and q hat, which is equal to 1 minus p hat, to obtain the estimated standard error denoted as sp hat and is written to be equal to under root of p hat q. This can be explained with an example as: what is the standard error of the estimator X bar in the following sample, where the values are 6, 8, 7, 10, 3, 5, 9, 8. So we have 8 values. What is the solution to this question? Let's look at it. Now sigma X bar is equal to sigma by root n. Since sigma is unknown, we obtain the estimated standard error S X bar equal to S upon under root n, and this comes out to be equal to under root of 5.143 divided by 8 and is equal to 0.802.
Thus, summarizing the whole as an estimator is a function of sample observations that can be used to reach an estimate of an unknown population parameter value. Also, we have learned a good estimator should give as precise an estimator or as precise an estimate as possible to be useful. We have also learned that if an estimator satisfies desirable properties of unbiasedness and efficiency, it is considered to be the best estimator. If an unbiased estimator is not available, then a consistent estimator may be used. Also, we have learned that sample mean is an MVUE, which is nothing but minimum variance unbiased estimator of population mean. So let me emphasize and say that we have learned that sample mean is a minimum variance unbiased estimator of population mean. Unbiased estimator of population variance is obtained by dividing the sum of the squares of deviations of sample observations from sample mean by 1 less than the total number of sample observations. The sample proportion is an unbiased estimator of population proportion. We would say that we have also learned how precision of an estimator is indicated by the standard deviation of the sampling distribution of the estimator.